Section 5.2, we started talking last time about multiplication and division with integers. In particular, we did the multiplication part. We also talked a little bit, I think, about absolute value stuff or inequalities. Properties, that's what we did. We talked about properties of integers. So we're going to take a look now at the division of integers. Integer division. For all integers a and b, a divided by b is the unique integer c, if it exists, such that a is equal to b times c. So, for instance, if you had something like -6, that's not going to work. We need the color. -6 divided by 3. The answer to that, of course, is -2, and the reason is because -6 equals 3 times -2. That's all this definition says. But the reason the answer is -2 is because 3 times -2 is equal to -6. We've seen this definition used before. We used it with whole numbers, and we've just now extended it to be true also for integers. And actually, it's true for rational numbers as well, but that's proportional and statistical reasoning, not number theory. So, if a divided by b is a unique integer, then the only reason that says if is because it doesn't have to actually work, right? It doesn't have to be an integer. So if it's a unique integer, then a is divisible by b, or equivalently b divides a, written with this notation, which we've seen before, right? But again, when we saw it before, we used it only in terms of whole numbers. And this actually just is extending the same thing we already knew to include integers as well. So again, if I said that I had -6 is what I used in the previous slide, divided by 3, and it is a unique integer, of course, because it's -2, then we would say that 3 divides -6, because it gave us an integer answer. That's what it means for something to divide something else. It gave us an integer answer. And of course, the notation for that would be this 3, it's a vertical bar, and then the -6. 3 divides -6. Inequalities. For all integers a and b, a is less than b, written this way, if and only if there exists a positive integer k such that a plus k is equal to b. And I hope by now you are feeling like, I think I've seen that before, because you have. You saw this same definition before, but with whole numbers. Didn't change at all. So what is different? Well, we can use integers here that are negative. So if I had something like -6 is less than 3, the reason that -6 is less than 3 is because there is a number that I could add to -6 to get 3 back. What would I have to add to -6 to get 3 back? 9. Magic number would be magic, I guess. But yeah, the magic number would be 9. Whoops. All right, so inequality theorems. For integers a and b, a is less than b, or equivalently, b is greater than a, if and only if b minus a is equal to a positive integer, i.e. b minus a is greater than 0. Okay, so we'll keep using the same numbers I'm using with my -6 and my positive 3. -6 is less than 3, because if I were to take 3 and subtract -6, what is 3 minus -6? That's 9. And that answer is positive. Right? The reason one number is bigger than the other one is because if you subtract them, you get something back. The reason 5 is bigger than 2 is because 5 minus 2 is 3. It's a positive number. There's something left over. All right, a few inequalities where I'm going to have to write some details down. The first one, x, y, and n are integers. If x is less than y, then x plus n is less than y plus n. So it'd be the same idea of talking about heights. We've talked about heights and shoes and, heels and things like that before. So if my daughter Abby is probably about 3 inches shorter than me. If we both put on 3-inch heels, she's still shorter than me by 3 inches, right? It doesn't change the difference in our heights. Now, on Monday, when she put on those heels and I didn't, my son, Eli, who's 9, was convinced that Abby was taller than me. We had to set him straight because that's not okay. She's only 12. Okay, next one. This one is something that's new. We haven't seen this happen before because we didn't have negatives before. If x is less than y, then negative x is actually greater than negative y. You probably remember this being talked about. You may not even know why, but the idea being that if you multiply both sides by a negative, you change this direction of the inequality. So the easiest way that you can argue that probably is from a number line. So let's think about from a number line, because if you have that kid, and you're going to all have that kid sometime in your teaching career who wants to know why. Why does that work? And we'll just use the numbers 2 and 3, right? 2 is definitely less than 3. You have no problem arguing that from a number line perspective. And here's 1, here's 0. So let's actually put the negatives of these numbers on the number line. Here's -1, -2, and -3. So if you keep the directions the same and now you're comparing -2 to -3, which one's smaller? -3 is smaller because it's further left on the number line. So the easiest way to argue this is to use very small, because it's easier to draw, but specific examples where you can actually see -3 is in fact less than -2. So the direction of the inequality must change when I'm writing it down. Okay, let me make this a little bit smaller. All right, next one. If x is less than y and n is greater than 0, then x times n is less than y times n. Now you'll notice it specifically said n's positive. So if I multiply by a positive number on both sides, the inequality stays the same. That's usually not the concern kids have. They're totally fine with inequality staying the same. But the second one here, where the n is less than 0 and the inequality switches, is a little more bothersome. Now, this is really just the general case of that, right? I mean, all the second example here was this case where n is equal to -1. So you could do the same thing with a number line if you wanted to with this and use the number -2 or -7 or whatever. I wouldn't go with -7 because you're going to have to draw a really big number line. But you could use another number that's not 1 and you could do the exact same argument from a number line perspective. Okay. All right. We have our last 2 examples for the semester. Are you guys ready for this? I know you are. Okay. This says to find all integers x, if there are any, that make each of the following true. Now, you know from what we've done in this class that there's no requirement that you use or solve equations in a traditional algebra context. So trial and error is okay. I'm going to show you from a traditional algebra context, but if you see the answer from a different perspective, that's all right. The thing you need to be careful of is to make sure that there aren't any other solutions that work as well. Because sometimes just because you found one solution doesn't mean you found every solution. Sometimes there's more than one solution to a particular problem. All right, so on this one, there's a couple of ways you could do this. Probably most of you are going to say that you want to distribute first. So if you distribute this first, you have -5x, and what is -5 times -3? 15, positive 15, and it equals -5. Okay, so if you're using equations, what would you do next?
Subtract 15 from both sides.
All right, so we're going to subtract 15. We're working in such a way that we're doing the opposite of what's already been done. If it's plus 15, we're going to subtract 15. So on the left side, the positive 15 and the negative 15, those are additive inverses, so we're left with the -5x. What is -5 and -15 added together? That is -20. So now I've got -5x equals -20. What's next? Yeah, it's division because the -5 and the x are multiplied. So I have x left on the left. What is -20 divided by -5? Somebody said positive. Positive what? 4. Now, what could you do to make sure that this actually is the correct solution? Plug it back in. Make sure it works. So let's double check. If I had the number 4 here, what is 4 minus 3? 1. And what is 1 times negative 5? Negative 5. So it works, right? Absolutely works. Another option, just so that you can see it when you're looking at it from here to start with, instead of distributing the negative 5, you could just divide the negative 5 to the other side to start with. And that would also eliminate the operation. Just another option. Okay, part B is a little more interesting. Part B says x minus 1 squared equals 1 minus x squared. So let's actually talk about these two quantities that are in here before we worry about anything else. Okay? X minus 1 and 1 minus x. What can you say about how those two are related to one another? And it might help to think about concrete examples. 5 minus 3, 3 minus 5, 7 minus 6, 6 minus 7. So take two numbers, subtract them, and do it in the other order, because that's all this is, right? It's two numbers subtracted and then the order of that switched. What happens when you do that? Right. The number is the same, the numerical value is the same, except one of them will be a positive number and the other one will be negative. Okay, so let's do an example. 5 minus 3 is 2, and 3 minus 5 is negative 2. And that will happen no matter what you choose, because x minus 1 and 1 minus x is the same thing, just the order switched. I mean, it's the reason we've talked about subtraction not being commutative, right? Because the number is the same, that's cool, but the signs are opposite. So whatever happens inside these parentheses, I'm getting the same value, except one's positive, one's negative. And then what does this operation say is going to happen to those numbers? You're going to square them. So what's going to happen when you square these two numbers? They're both going to be positive, and they're going to be the same, right? Now, does it matter what x is? Not a bit. X can be anything and make this work. So the answer to this is that x is any real number. It's any number at all. We're working with integers, so you're probably going to write down x as any integer. Okay? Any integer works for this. Now, let's say you don't see that at the beginning and you're trying to solve this from an equation standpoint. So let's actually look at how you would do that, okay? By solving this from an equation standpoint. Right now you've got two quantities and they both have squares on them. Okay, and we're trying to work our way out of this mess so that we get x equals when we're done. So what could we do first to this as an equation? Square root. Okay, so we're going to square root. So on the left-hand side, I get x minus 1 because the square and the square root cancel. On the right-hand side as well, I get 1 minus x. Fabulous. I don't have squares now, right? So what's next? There's a couple options.
But the x is on one side, so maybe like add x to or something. Yeah.
Okay, so you'd like to do like this?
Yes, yeah, add x to both sides.
Add an x to both sides. Okay, so now I have 2x on the left minus 1 equals, and on the right, what do I get? I get a 1, right? Now what? So now I have 2x is equal to 2. Yeah, so the solution's weird because we just talked about it should be able to be anything. And now we just got that the answer's only 1. That's sort of weird, right? Any idea why that happened? We made an error along the way. Do you know what the error was? Nope, doesn't have to do with parentheses. It has to do with square rooting a squared quantity. So let's pretend for a moment that the x minus 1 inside of one of these, I don't care which side it was a negative 2. What happens when you take negative 2 and you square it? It becomes a positive 4. But then when you take the square root of positive 4, what do you get? You get just 2, even though you should have gotten negative or positive, right? Because when we put square roots into an equation, I don't know if you'll remember this or not from algebra, but somebody somewhere along the way told you that if the square root's there already, you can just take what they call a principal square root. So the square root of 4 is 2. Square root of 4 is 2. But if you put the square root into the system, if you're the one who introduces that, you have to put the plus or the minus. Do you remember that? That's what we missed here. We missed the plus or the minus. When we inserted the square root, one of the options was exactly what we did. The other option was where we had a minus. So here's what we're missing. I'm going to make this smaller so that I have more space to work. This is totally correct. It's just only one option. So I've got an or here. The or is going to look just like the original one. But on one side or the other, I don't care which one you put it on, you need to put a negative. Now, technically, there's 4 things we could write down. We could write down the original parts that we had. We could write down negatives of the original parts we had. We could write down a negative on the left and a positive on the right, or a positive on the right and a left and a negative on the right. There's 4 things we could write down. But really, if I just put a negative on both sides, isn't it just the same thing as I already did? Yeah. And if I put a negative on the left or a negative on the right, but not on both sides, isn't that the same thing? It is. So these are really the only 2 distinctly different options. So let's see what happens when we do this option. I need to distribute the negative through, right? So I have x minus 1 on the left, and I have x minus 1 on the right. Now, if I actually try to do what we did in the last problem, and I tried to get the x's together, what's going to happen? They cancel out. All of a sudden now I have, negative 1 equals negative 1. And is that true?
Yes.
It's true. So whenever we end up getting no x's in the equation, or 2, you could even stop here. It would totally be fine. Here's a good spot to see it at. But 2 sides where they're exactly the same already, like visually you can see it. At that point, it means that it's all, we'll say all integers because we're only working with integers. It's really all real numbers, but all integers will work. Okay, so you don't have to solve them. I wanted to show you 2 perspectives. The first way that we did it, some of you had eyes glazing over. You're like, why is she talking about this? Why isn't she just solving something? I know, and I get that. But if you saw it from the first perspective, it was a whole lot easier, and you were less likely to make a mistake. Because the chances are pretty good that this is the work that you would have done had you just solved it. And you would have been wrong, correct? You would not have gotten all of the possible solutions. So do be very careful. Those weird things usually happen when there's squares involved. I'll tell you that. Squares and square roots involved, they just get weird stuff happens. So just be a little bit more cautious with those particular problems.